Hello, everyone. Welcome to today's show. And if you are joining first time for this segment, this is the interview series that we do every Friday between 8 a.m. to 11 a.m. Eastern, depending upon the availability of the guest as well as time zone. And for today, we have ultra special guest Michael Azoff from Omdia, and obviously that's a very reputed analyst firm. And by the way, the topic today that we have is going to be super intense and heavy, so make sure you guys grab some coffee. On that note, Michael, do you want to introduce yourself?
Yeah, thanks so much, Sam. Hi, hello, everybody. It's good to be on this show. So I am Chief Analyst in the Cloud and Data Center practice here at Omdia, and I cover all things software development in the group, and with a focus on AI. But I've also been doing a lot of research on AI beyond my work at Omdia. And I used to build neural networks back in the day when backpropagation was the big thing in 1986. I go back a long way, Sam. And I wrote a book in 1994 on neural network time series forecasting. And that was a very hot topic at the time. And I've seen how neural networks have evolved since those days. And I've recently written a book on human level AI, how neuroscience can inform the pursuit of artificial general intelligence. So, yeah, so I've got a lot of background in AI. So yeah, I'm eager to talk about it. Yep.
Yeah, so thank you so much for being here, Michael, once again. And I cannot wait to hear about Neural Network Friday morning. I have my extra dose of coffee today myself. Just 1 second, I want to speak to my audience. And audience, if you're listening to this, then obviously this is a three-way conversation. So make sure you guys share your comments, stories, any questions that you might have. Michael is a very knowledgeable guy, so you want to utilize as much time as possible when you comment or post your stories. We are going to bring them and discuss them. That's going to be our priority. So Michael, so neural network, I mean, you said that you have been building this for a while, so maybe talk about that a little bit. I mean, is it more than cooking an omelet in the kitchen, or or easier, I guess?
Right. So the evolution goes back to Rosenblatt in the 60s,
Yeah.
and who came up with this concept of having layers of neurons connected and data being presented to the network and flowing through, and you get an output. And then you compare that output with what you know it should be, so you get an error signal. But the challenge was how to use that error signal to train the network. So they had an interesting concept, but they lacked the method for solving anything other than a single layer of neural network. If you had two layers, for example, there was no method for between the input layer where you present the data and the output layer, how to train that hidden inner layer. That was the real challenge. And the trick was quite remarkable in a way, because the early neural networkers, Marvin Minsky, for example, was a prominent one. They were using step function thresholds at the neuron. So the function at the neuron was that you collected all the signals, and once they hit a certain threshold, beyond that threshold, you'd get a positive signal coming out of the neuron. And that function was a step change. Now, if you integrate that, you get infinity. And what a number of researchers realized was that if you smoothed out that step function with a sigmoid, and you could make that gradient quite steep, but it can still be smooth at the corners. And that sigmoid allowed you to have a differentiation, a gradient that you could calculate. And that was the breakthrough, because once you can take gradients, then you can use calculus to come up with a scheme for moving that error signal from the output layer back through the network to adjust the weights, the weights which attenuate the signals between the connections between the neurons. So you start off with random weights, and then you iterate thousands, millions of times and you make the little adjustments using that calculus rule of backpropagation until the weight converge towards values that will give you a minimum in the output signals. So across all your training data, you collect all the errors and you try to minimize that total. And that's essentially being done today with large language models. So this concept of the backpropagation goes back all the way to 85, 86 when they came up with this algorithm. Um, and neural nets went through a number of evolutions.
Yeah.
A major one was the AI winters when the funding stopped, so that was one major sort of hurdle. Backpropagation created a restart, but then that sort of died towards the late 1990s, and Jeffrey Hinton and a few others carried on working, and they used this label of deep learning to sort of hide the fact that they were still working with neural nets. It was a strategy to get the funding and the grants, but basically it's neural networks, the same neural networks. But it came up with a lot of very interesting novel ideas with deep learning. A lot of the heuristics that were used back in the 1880s and 1990s were sort of turned upside down. For example, back in the old days, we had very little data. So we tried to build very small neural networks so that the neural network wouldn't sort of over learn the data. You wanted the neural net to generalize on new data, on test data. So you built as small a model as you could for the data that you had. That was known as the curse of dimensionality because there was not a lot of data. With big data, with the internet and big data, suddenly there was a huge amount of data. So you could build bigger models, and that's how deep learning sort of came on the scene. By 2020, by 2010, they had designed neural networks with a lot of really remarkable heuristics. Because I talk about heuristics because there's a lot of empirical research done with neural nets. There's a lack of theory, but a great deal of empirical research that came up with some great rules and algorithms. So they basically built these huge models which they could then adjust so that they didn't over learn the data, and so that the generalization performance was good. They used pruning. They
Yeah.
used ways of reducing the number of neurons once they had created a model that was giving a reasonable answer, and so on. So um, if you put together all of these techniques, you end up with some really great models. And the breakthrough now, the challenge was, of course, that they were working with these very large networks, which were very slow to train.
Yeah.
So the breakthrough was when NVIDIA came up with this general programming on GPUs, because somebody had the idea that. So we need to understand that the parallel story that's going on here with Moore's
Yeah.
law and with CPUs, and that basically, you couldn't turn up the frequency in the CPU because it was basically going to melt the device.
Yeah.
So you started to have multi-core CPUs, but they couldn't quite compete with the multiple cores of a GPU. It's obviously the cores are not the same as a CPU, but they were used for video processing,
Yeah.
and that's how NVIDIA and others sort of grew in that sphere to create those boards for video games.
Yeah.
You've got this situation that uh, uh, um, Jensen Huang sort of understood that there was a limit of Moore's law on the CPU front, but the GPUs were getting better and better, and somebody had the idea of allowing general programming to run on these GPUs, and he saw the opportunity within his company. He said this guy was brilliant because it was a great idea. He made those GPUs available in the market.
Yeah.
Jeffrey Hinton's group grabbed that opportunity, ran a model that they were working on to detect objects and label them. So this is like a classic test in in computer science, object recognition.
Yeah.
Um, and so there was a standard test that was run annually, and you had uh, uh, professors in computer science who dedicated their whole career using handcrafted algorithms to detect objects in an image. And they were all competing with each other. And here comes along a group from Jeff Hinton's AlexNet, which these guys didn't know anything about computer
Yeah.
science object recognition,
Yeah.
but they obviously were the world's best at neural networks, and they submitted this neural network that was trained to
Yeah.
detect objects, and of course it was better than any other algorithm that was presented in that benchmark competition. And then the world changed after that, because and the critical thing that I should say, so you've got all these parallel things happening, right?
Yeah.
But the critical thing was the the GPU when they port. So the fact that you could do general program on GPU meant you can train the neural net
Yeah.
on a GPU. And there was a very good fit, because there's a lot of parallel processing being done when you're training a neural net.
Yeah.
So this was ideal to port to that GPU, and it reduced the training time from weeks to hours. And obviously, if you're doing research, you're getting feedback within an hour, not a
Yeah.
week or a month. That makes all the difference. So it accelerated the pace of research. The algorithms were superior to anything that people were doing in terms of handcrafted algorithms for object detection. So this really proved that the neural net approach could be very, very good. And really that started everything. And you can trace the evolution of where we are today with large language models to that launch of deep learning back in 2010, 2011.
Yeah.
Sorry, I've got on a bit, but there's a
No,
lot of
this is
history.
great.
There's a
This
lot of
is
history there.
no, this is great and great context. Thank you so much for sharing that. So
Yeah,
let me digest that, and obviously, I want to give you a little more context from our community perspective, because we want to make sure that people are able to follow along, right?
yeah,
So our community is primarily business community. I mean, they sort of understand neurons, but personally for me, even though I'm an engineer, it's been 22 years since I studied that. So so maybe provide some more context from the business perspective.
sure.
Research is great. What does it mean for my CFOs, COOs, who are listening to this? I know that, I mean, obviously the OpenAI is great, and again, you are arguing that it's all because of that hardware innovation that they have done. So what does it mean for them as of today, and what do you see now that that has been done? Maybe in the future there are going to be similar innovations that are going to come out. I don't know if algorithm is going to be more efficient. So tell us more about this from the business
Sure.
perspective.
Okay, so I've encapsulated a lot of history in what I just said, but I should focus now, and especially with the interest today of AI in a business context,
Yeah.
large language models, right? So this was there was a paper that was written, I think, back in 2020 from Google, a Google research team, and this really spurred a lot of research around these large language models, um, and ostensibly they sort of predict the next word in a sentence. So they trained on basically all the data that exists out there on the internet. So there's a lot of text, a
Yeah.
lot of language, multi-language. It doesn't matter what language it is, but they are seeing how people with intelligence put words together,
Yeah.
right? And that intelligence is encapsulated in the higher dimensions within a neural network.
Yeah.
And this is why these neural nets, these large language models, can understand, because they have captured patterns of thought
Yeah.
that exist in text, in words, in
Yeah.
how we put words together. They semantically map the concepts that are embedded in sentences, and those connections between concepts, they map all of that. And so they're able to understand
Yeah.
how to use language, and this is absolutely an amazing breakthrough.
Yeah.
So that's one major step forward. Okay. The second one is emergent properties of these large language models, because once you reach about 10 billion neurons,
Yeah.
so you can actually see in one of the early papers a graph of how when you add more neurons to the model,
Yeah.
once you get to a critical point around 10 billion neurons,
Yeah.
they start to be able to do something that we've never seen before.
Hmm.
And I think this is really why everyone is sort of excited about
Yeah.
the potential for artificial general intelligence,
Yeah.
because they can reason, they can pass the lawyer's exam with flying colors better than a
Yeah.
human. They
Yeah.
can do mathematical proofs. There's a whole range of different disciplines where they shine so well, right?
Yeah.
And there's a great Stanford University produces annually the AI Index report to show how benchmarks are run through these latest models, and you can see that in the last few years, these with these benchmarks that are designed to be difficult for computer models, right? That they surpass the capability of humans. So there is something really significant here. And coming back to your question about what is the implication for business,
Yeah.
we need to divide what is happening in AI into two parts. The bit where what have we got today? How can we apply it in the enterprise
Yeah.
versus continuing AI research towards that ultimate goal of human level AI.
Yeah.
And they are two quite separate things. So let's talk about the business side of things,
Yeah.
because where we are now with
Yeah.
these large language models is good enough to be used in the enterprise
Okay.
in a whole range of different ways, and they are already being used in many practices. For example, paralegals in a legal, they now use AI to do searching for documents,
Yeah.
to extract documents and information, which paralegals used to do.
Yeah.
Doctors, when they're finishing surgery with a patient, they have to write notes. So now they can ask the AI to summarize the conversation that's
Yeah.
just gone through with the patient. I mean, there's just so many different ways in which AI is helping. I mean, software development. So this is an area that I'm working in at Omdia to do AI-assisted software development
Yeah.
product comparisons. I've just written a report
Yeah.
on this very topic, very hot topic, a great application for AI in the enterprise, coding assistance. Um, so there's just many, and I think that this is very significant in terms of how businesses are going to run, because today, I mean, yeah, we've computerized a lot of systems, but there's still a lot of paperwork
Yeah.
and a lot of manual processes and business processes that are designed in ways that haven't changed for decades.
Yep.
Now we've got an intelligent machine, and there are so many opportunities to rethink how we do business processes.
Yeah.
And I think we're just at the beginning of that. So it's very exciting for enterprises, I think. Also a little bit scary because people, there's going to be change, there's going to be disruption.
Yeah.
Um, so, but it's also exciting. So I think that there are great opportunities, but people do need to enterprises. So this is I would say this is a key message for the enterprise. They do
Yeah.
need to grapple with this. Don't look away
Yeah.
and think about it later. Start dealing with it now, because the change is happening and it's changing very fast, and the pace of change is fast. So start grappling with the issues now of how you can exploit this technology to your advantage within your business.
Yeah, so very interesting. So I want to touch on some of the layers that you have mentioned. So the underlying principle, if I understand this, so you are saying one of the breakthroughs that has been there with this technology is now they have figured out how to associate words together, and that's what humans were really good at. for the most part. But if you look at human brain, I guess human brain does far more than just associating words together. I don't know, so are there going to be any sort of technical limitations with this technology? Because my assumption is going to be that we do far more than just associating words. I don't know, if it is similar, everything that we do in terms of thinking, reasoning, doing any sort of computations. I mean, we do a lot more, I guess. So in your mind, do you see everything being just the associative or associating of words in this context, or do you see more?
Yeah. So in a way, this comes back to that other half of what I was referring to, the sort
Yeah,
of two sides to AI, the
yeah,
research towards the ultimate goal of human level
yeah,
versus what we can do with this technology today in the enterprise. So yep, we can use the LLMs with their capability in many ways within businesses,
yeah,
but to your question, how intelligent are these machines really?
yeah,
And I think we're still at a very early stage. I mean, to give you, I mean, there are so many ways in which you can contrast the human brain, which are our best example, obviously, of intelligence versus the current machines.
yeah,
So when you don't present a query to the large language model,
yeah,
what is it doing? It's doing nothing, right? It's
yeah,
brain dead. I call
yeah.
it brain dead,
Okay.
right? Now, if you stop all sensory information
Yeah,
coming into your brain, so you might be in a sensory deprived environment, one of these chambers where you're lying on a pool of water and you're floating, and
yeah,
um, so when all the sensory information is stopped, your brain is still very, very active.
it is.
And when they do a lot these MRI monitoring of the
Yeah,
brain when you're asleep,
yeah,
the brain is all the time working.
yes,
There is no change in
yeah,
terms of activity. It is functioning.
yeah,
Neurons are firing all the time.
yeah,
So even when you're asleep, so uh, you know, the the point is that it's what we can think of as an inside out model versus an outside in model versus an inside out model. So outside in model is like the current AI.
yeah,
It's waiting for an outside signal to come in and it processes it and you get an output. An inside out model is one which is active internally, and it's interacting with the external world to find out what is out there
yeah,
and gather information and so on, and bringing that information back into the inside. Um, and the consequence of this perspective is huge. And at the moment, the AI models that we have are all outside in models. They're not inside out. So that's the first challenge, is to have some kind of continuous loop going on
yeah,
in the AI model, in the artificial model, that is doing something. And in my book, so I've written a book on human level AI, as I
yeah,
think I mentioned. So one of the suggestions I make there is that you make the model a scientist, because I can't think of a better function for an artificial being, an artificial model, is to be a
yeah,
scientist who's out there trying to learn what is out there, be curious, gain knowledge,
yeah,
and that would be a great continuous loop function in a robot,
yeah,
is to explore and learn. And so that's one thought. Um, but we can delve into the neuroscience, because there are challenges in neuroscience in understanding the human brain, and I think that AI research can help the neuroscientists and vice versa. I think the neuroscience can help the AI. So, but there are gaps in both. So in neuroscience, there's a gap between the empirical data that is gathered in neuroscience, and there is a vast ocean of understanding and data that has been gathered at the molecular level, at the synaptic level, the electrical signals, the chemical signals, the neuromodulators. I mean, the vastness of that empirical data is so huge that um, um, Terence Sejnowski, I think, was a scientist who he crossed a number of disciplines, and he latterly worked in AI, but before that he worked in neuroscience, and he basically said that once you start working in one of these disciplines in neuroscience, it's like you're going down a rabbit hole. It's very difficult. Yeah, seriously, it's very difficult to come out again
Yeah.
because it's so deep and there's
Yeah.
so much and there's so much detail.
Yeah.
And this is the challenge that they have, is that you've got all this research going on
Yeah.
at that empirical level, and then there's this big gap, and then you're at the cognitive psychology level where
Yeah.
there's a lot of understanding of the human brain at a sort of psychological level,
Yeah.
and then the gap is between the two. How do you relate what is happening with neurons firing and
Yeah.
all that learning that is being gathered? How do we relate that to our higher cognitive abilities? So neuroscience has this problem that they don't have an overarching theory that explains how the brain works. That is still a major gap. And the same exists with AI,
Yeah.
because we have our existing models, but it's still missing quite a
Yeah.
lot in terms of how we get to artificial general intelligence. Um, and I think the two can work in tandem. I think the progress that can be done at a pure AI a research level can help understand on a neuroscience side a sort of more systems level approach, because you need a systems level understanding of the human brain, and
Yeah.
we just don't have it.
Yeah, so very interesting. So, if I could summarize what you just mentioned in one word or maybe two words, I guess, it's probably going to be continuous learning, which is kind of missing with these AI models. And I don't know if we are going to get the continuous learning later on. Right now, one of the things that I was reading about AI is that once the model is trained, after that it's not learning at all. It retains the context when you interact with these queries, but as such it does not retrain. So that's my understanding of these AI models. So once it is trained, it's trained. No more learning anymore. I think it might be learning with additional data, but as such it's not learning from the additional queries that you are sort of interacting with. It's not retaining any of the information that you are feeding to the algo. It only retains inside that session, and it kind of captures the context based on that. So I don't know if in the future, do you feel that these models are going to grow and they will have a lot more continuous learning? But my fear with that is, once you do that, you are going to introduce a lot more noise. And even today, and again, I think this is coming from the same article or different article. They were saying that internet is full of noise. And if 90% people are saying some garbage things, that sort of becomes truth, because what AI is doing is AI is trying to generalize what 90% of the websites or people are saying, and it simply is making that truth, and sometimes that might not be truth. So there's a real problem here. So do you see that as a problem? Do you see continuous loop created, I guess, or included as part of the future AI algorithm?
Hmm. Well, there's a number of issues that you've raised there. I mean, in terms of the learning, with large language models in particular, it's
Yeah.
possible to extend their scope through retrieval augmented I forget RAG,
Yeah.
retrieval augmented generation.
Yeah.
Look it up. But the point about RAG is that you can add a vector database. So you have semantically mapped a private database, say your corporate records, to talk about the enterprise context.
Yeah.
So your corporate database, or if it's your looking at code assistance, your code base, and you vectorize it into a vector database, and then you can use that as part of your prompt, so that the large language model, when it's searching for an answer, is able to tap into that vector database
Yeah.
to enhance the answer. So it is possible to extend the capabilities of large language models, so that and there's also fine tuning is another technique where you retrain, and that involves more resources, but you can retrain part of a large language model with new information.
Yeah.
So example, you can add an extra layer
Yeah.
on top of a large language model to make it specialized for a particular discipline. So with large language models, there isn't that sort of catastrophic forgetting that was a problem with a lot of earlier era deep neural networks, that you train them for one thing, and then when you wanted it to do something else, you had to retrain the model, and it would forget what it had learned before. So large language models are more versatile in that respect. I think the other thing that you touched on is that, and this is something to do with the fact that, okay, so the large language models today have learned everything on the internet. So
Yeah.
where's our next source of data? And the danger there is that a lot of content is appearing on the internet that's generated by AI.
Yeah.
So now you're sort of wondering, well, we had information that we knew came from humans. What does it imply that now there's information going out on the internet that's originating with other AI?
Yeah.
And the reason why they need all this data is because they're building these even larger sort of trillion, of the order of trillion neurons, and you need more data to train them. Now, you can create synthetic data, and that's obviously a technique that can help. But yeah, we're sort of reaching limits, and it is a challenge, um, which is not to say that data generated by AI is necessarily bad data.
Yeah.
I mean, but it's interesting that we've reached this point where we're sort of running out of data, and we need new sources. Um, but yeah, and there's a lot of techniques now to actually reduce the size of neural nets and still make them high performant. So yeah, I mean, we're right at the bleeding edge with these questions.
Yeah, so very interesting. So let's talk about your resource comment that you just mentioned, that you can overlay sort of this vector database, and the algorithm can use that as well in conjunction with what is already trained. Now you mentioned the resource constraint. So resource constraints are going to be at the model hardware level, or is it going to be on person's computer? Where is this vector database sitting, and where is the computation happening? And are these constraints, the constraints that you are mentioning, are these because of the edge devices that we have, such as the computer in which you are firing up the queries? So I don't know if that is the bottleneck, or the hardware, underlying hardware for the continuous learning is going to be the bottleneck.
Yeah. So I think if you're using RAG, then it's less of an issue because you're not retraining anything.
Yeah.
So it's retraining a neural network, a large language models, or any neural network that is resource hungry.
Yeah.
And obviously, to create a foundation large language model consumes billions of dollars of compute time. So with RAG, you don't need to do that. So RAG is a very popular technique
Yeah.
for enhancing a lot of solutions out there. And as I say, I've been looking at code assistants, AI-based code assistants, and nearly all of them have got some RAG capability, or will
Yeah.
have them on their or have them on their roadmap. So, that's a very good way of enhancing a model. Um, the more resource hungry is the fine tuning, where you may add a layer to a foundation model, but that involves retraining, and that can be more expensive and needs more resources. Um, I think also there is the demand on inferencing. So if you've got a chain of thought um, type of model where you prompt the model with a query,
Yeah,
and then you iterate a few times, so you get the model to look at its response and then evaluate it and see whether it can enhance it. And so you have these sort of multiple iterations with chain of thought
yeah,
models, which is quite compute intensive. If you think about millions of people trying to inference a model that's out there as a service on the internet, on a cloud. So you do need a lot of resources to run these models. And Which is why there's also a lot of interest in having smaller models that run more efficiently, that you can
right.
actually deploy locally on the edge,
Yeah,
in a manufacturing plant or at a retail outlet, whatever the application is in a smart city. You want to be able to put these models on the edge and have them work locally and respond very quickly. So lots of different scenarios, and I think there is a lot of research being done on small language models, that are still very, very good and can perform their function.
very interesting. So let's talk about the vector databases a little bit, and that's fairly new as well, as far as my understanding goes. I don't know which year the vector databases became popular, but do you believe that that could be another factor which may have contributed towards the AI success?
Yeah, I mean, so it's being able to map um, uh, the information,
Yeah,
and semantically map it has been around for many years. There's a lot of research. If you go back into the literature, there's a lot of research teams in universities. There's even some commercial companies that have got these sort of semantic mapping.
yeah,
Um, but really, the vector databases sort of came into their own in the last few years because they were seen as a way of enhancing large language models,
yeah,
and so there are these models that can convert human readable text into a vector database. So they map the semantics, if you like, that's
yeah,
embedded in the text into this vector database. So the the vector database, each vector is they're just numbers. If you looked at them, they wouldn't be meaningful, but they're
yeah,
meaningful in the context of that mapping, that in that cement so that it's hyperdimensional. I mean, it's a fascinating topic.
yeah,
um, and so they're able to map, to connect these with the large language model, so that a
mhm,
large language model can then search for information in that space.
yeah,
And it is great science. It is great progress,
yeah.
but the history of it goes back many years.
Yeah, so let's talk about DeepSeek a little bit. And I don't know if there is going to be some sort of technical explanation that you might have, why they were able to accomplish that in a very resource constrained environment, but the algorithm was very efficient. I don't know, it's just hype, or were there any sort of technical merits to what they have done? And do you see that getting replicated with the other models as well?
Mm. Yeah, so there's no doubt that the team in China,
Yeah,
and my understanding is that the leader of that group was a hedge fund. He had a hedge fund, so he
yeah,
had a lot of money to put behind his research,
yeah,
and he basically took the top AI engineers from Chinese universities, and they basically created this amazing hothouse team
yeah,
who just had a single goal, is to create a really super large language model. So, great credit to them. Um, I'm not sure that DeepSeek. I mean, DeepSeek is now at the leading edge in terms of performance, and competes, with the best models from other research teams, OpenAI, Anthropic, DeepMind. Google Gemini. I mean, so they're all up there. So DeepSeek is up there with the best of them. I don't know whether it's necessarily better.
Yeah.
Maybe one day it is, and then somebody comes up with a different model the next day.
Yeah.
I think where the hype is around the thing that they were saying that it was cheaper to train it
Yeah.
with their approach. Um, until another independent AI group is able to replicate that kind of uh, low resource training, I'm not convinced that that's how they did it. So we can take that as marketing hype until we see better evidence. But I don't think it's really well. I mean, let's put it this way: if
Yeah.
they really can train these models with a lot less GPU power,
Yeah.
then that would be very interesting. But we need independent corroboration of that. So I would put that. I would leave that with a question mark.
Yeah, so very interesting. So I guess energy is another topic that you talk about, that the major limitation right now in terms of the accomplishment, I guess, or progress, is the constraint is really energy, right? So what do you think, is going to happen? Are you forecasting that there are going to be some innovations from the energy perspective, and because of which now we are going to see a lot more progress with these models, and maybe 10 years, 20 years? What's your take on energy?
Yeah, so this is a really a topic that's very dear to the heart of my
Yeah.
colleagues. So as I mentioned, I'm in the cloud and data center practice. I'm on the software side, but my colleagues are mostly on the hardware side, and they deal with building data centers, which has gone absolutely exponential. It is
Yeah.
such a hot topic at the moment. We recently finished Data Center World, an event run by our parent company Informa, and they had twice as many delegates as last year, and last year was pretty mega already.
Yeah.
So the world is going mad about, over data centers. Everyone's building them, and it's to basically run AI workloads. That's really the prime motivator. The people see what's happening, and they are planning for the future. So there is this scramble to build enough data centers to run these models, and yeah, I mean they're going to run out of energy at the current pace, and you have Microsoft and Google and
Yeah.
Amazon talking about building nuclear power stations at the these small modular reactors um, at the location of the data centers. Um, I mean, I so to my mind, it's and Nvidia keeps building more and more powerful GPUs which are more and more power hungry.
Yeah.
Um, if you look at the human brain and see
Yeah.
how much it consumes,
Yeah.
a human brain consumes the power of a light bulb, about 20 watts.
Yeah.
Okay, so shouldn't we go back to neuroscience and find out, well, how does the human brain use so little energy to do
Yeah.
this kind of computing? And then you look at how the brain sends signals between neurons, and they're spikes, they're not continuous signals.
Yeah.
To send a continuous signal between two neurons consumes more power than if you just send a wave down a channel.
Yeah.
So already you can see how more efficient the human brain approach is compared to these digital models.
Yeah.
Um, so these spiking models, neuro computing approaches, um, I think there's a lot of promise in modeling with spiking networks, and I'm seeing more papers being published in that area,
Yeah.
and I hope that they're not starved of research funding because of all the interest in LLMs at the moment.
Yeah.
But I think that um, my hunch on the future of achieving AGI is that we'll
Yeah.
use some kind of spiking neural network, which will be a lot more energy efficient,
Yeah.
and we'll get over that sort of challenge of limitation of energy.
So, in your view, and I don't know if the enough research has been done, or if you are going to have any answers for this, but were there any sort of technical limitations for not considering spikes from the get go as opposed to the continuous signal? Is continuous signal easier? So, what's going on here? I guess maybe break it down a
Mm.
little bit.
Yeah, definitely. It is easier to model having a continuous signal. You just have
Yeah.
a one appear at a node, and
Yeah.
it's there.
Yeah.
You don't need to model the time as such. I mean, you have your pace of iterations, which in effect is a kind of time, if you like.
Yeah.
But it is more complex to model, and this is why there's the community that's working with neuromorphic computing. Let's use
Yeah.
that term for
Yeah.
spiking neural networks. They try to build hardware, and the
Yeah.
trouble with building hardware is that it's fixed. You build a model and
Yeah.
and it's fixed, and then you want to make a change, and
Yeah.
it's rather expensive to
Yeah.
to now change it, right?
Yeah.
And
Yeah.
this is why software works so well, because you can change it very easily.
Yeah.
And so you have to try and build a neuromorphic computing hardware that is
Yeah.
flexible enough to allow for changing for different models, different ideas, without sort of hard wiring assumptions, which you then will want to change. So it is more complex, it is more difficult, no doubt about it. But it hasn't stopped the research happening. So Intel has got their low-high models, which they give out to research community to
Yeah.
to 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 work with. There's a Spinnaker model that is funded by the EU. There are models there, so they're building hardware arrays for spiking nets, and I think as I mentioned, my hunch is that these models will be the breakthrough. And I should mention memristas in this context, because memristor technology has been shown to be really useful in these sort of hardware models for neuromorphic.
Yeah.
And there are challenges in manufacturing memristas at a economical way and at a scale. But once they overcome these manufacturing hurdles, then I think that breakthrough with memristas will flow through into the hardware that's being used for neuromorphic computing. And I think that will be, once that happens, that will create a step change. And I think there'll be a jump in the capability of that side of AI. So yeah, watch this space. I think that's going to be an interesting one.
Yeah, sorry. So, which manufacturing hurdles are you talking about? Are these resource related, or so
Well,
tell us more? Yeah,
yeah. So memristas, embedding memristas in the neuromorphic hardware is
yeah,
is one approach that's very promising. And there's a company called Rain Neuromorphics,
yeah,
and some leading AI researchers are involved in that project. But really, they need memristor technology to be able to be fabricated at scale
yeah,
and at a low cost. So it's a manufacturing challenge. It's about materials science. And I think once they have that breakthrough with memristors,
yeah.
and they can build these large scale memristor arrays, then I think that will be a breakthrough. And I think we're going to see a step change in how neuromorphic computing can help here. So
Yeah, very interesting. So let's go back to databases a little bit more. So I know that there has been a lot of change in the database world as well, and I don't know if you cover databases or not. But when you look at, so for example, vector databases are new, graph databases are new. They have changed a lot of things, right? You look at the traditional relational databases. I don't know if there have been any sort of changes in attaining the transactional integrity. I don't know if the fundamental assumptions of the CAP theorem, which actually drove which databases are going to be right fit for which particular context. I don't know if there are any changes to that. there are some commercial applications that are sort of claiming that they are using these some of the either vector or graph databases, and they are claiming that they have transactional integrity. I don't trust them, uh, to be completely honest. So have you seen any changes to that, any changes to cap theorem? Do you think even relational databases are going to see some sort of changes?
Hmm. Okay, well that's a topic all of its own, right? I mean,
Exactly.
databases, there are so many different types now.
Yeah.
And my take is that choose the right database for the task.
Yeah.
I mean, if you take, for example, cloud native computing,
Yeah.
and how uh, you need to have fast changes, which the atomic type of relational database is too slow. So you have what they call in the world of cloud native databases eventual consistency.
Yeah.
So you've got all these different approaches that you use depending on the technology that you're applying.
Yeah.
Um, so it I think it's really a case of um, having an understanding of what is the task, and
Yeah.
what and knowing the array of choices for databases, and then just picking the right one. And I think the nice thing is that that some of the latest databases out there, dare I say Oracle, they give you the choice of whichever model you want,
Yeah.
out of one box. Um, and then there are the pure plays, the MongoDB and a whole bunch of others, which have made particular types of NoSQL their own. I mean, there's just so many,
Yeah.
and you really need to. Yeah, you should probably speak to a database analyst.
Yeah, we can definitely cover. Yeah.
I don't spend enough of my time on databases to give you a sort of ultimate um,
Yeah.
reflection, but I can just say that there this space has exploded
Yeah.
in the last 10 years. I mean, it's
Yeah.
just incredible. I've been working as an analyst for 20 years,
Yeah.
and when I started 2003, it was very easy.
Yeah.
Relational database was the king.
Yeah.
And now there's just so many
Yeah.
that I think and it really is a case of choosing the right database for the task,
Yeah.
and switching when you need to, depending on what your needs are.
Yeah, exactly. And since we were talking about databases, that's why I brought that topic.
Yeah, yeah,
We
yeah,
can
sure.
probably can cover that in detail some other time. But yeah, from the AI perspective, did you want to cover anything that you could not cover as part of this episode?
Well, so I guess we got a few minutes. Let me just put this thought out there about
Yeah.
consciousness, okay?
Yeah.
Because that is really one of the big, you know, the idea of consciousness in neuroscience was taboo for a long, long time, because you know how it is with science, that you deal with what you can deal with.
Yeah.
If you can grapple with a problem, and you have a way of researching it, that's what you do. And if you
Yeah.
have a topic like consciousness and you have no idea how to deal with it, you just put it aside. And if somebody comes up with a research proposal to study consciousness, you tell them to go away. So it was taboo. It really was taboo. Uh, Suddenly, it all
Yeah.
changed,
Yeah.
because with MRI, non-destructive monitoring of the human brain,
Yeah.
because back in the old day, if someone was having brain surgery, you, there's no nerve sensors inside the brain, right? So you could put probes inside the human brain,
Yeah.
and you could ask the patients, look, do you mind if we do these experiments while they remove a tumor from your brain or something? And the people would say, yeah, go ahead. And they would have that's how they did experiments.
Yeah.
Now you can do non-destructive experiments using MRI and all these monitors, and all of a sudden you can start looking to see, well, how does consciousness start?
Yeah.
What's the signature for consciousness? So all of a sudden it became a respectable topic, and it really is a fascinating one. I've made some suggestions about how we can perhaps start with the kind of consciousness where there isn't self-awareness, because I think
Yeah.
that's easier to deal with. And we see that in the animal kingdom. And I think that it's something that, if you look at the evolution of human life
Yeah.
and the human brain through evolution, because all biological life shares the same kind of neural net model. If you look at an insect or a mouse or a bee or a lion or a human being, we all have the same kind of neural net,
Yeah.
So from an evolutionary point of view, we all sort of evolved, and initially we had a kind of consciousness that didn't have self-awareness, and you can do tests with animals to see whether they have it or not. And I think that if we can model this kind of awareness, which I think there's a strong link with that and visual processing in the brain.
Yeah.
If you can model that, that's like a stepping stone towards ultimately understanding what consciousness is. But it's a big topic.
Yeah, that's very deep as well, I guess.
It is, yeah, yeah. But I think one of the points that is interesting is that you can have intelligence without consciousness,
Hmm.
to a limited extent, but to do that higher executive planning and vision,
Yeah.
you need an element of consciousness,
Yeah.
and let's start with consciousness without self-awareness. with with awareness, that's a bigger challenge. Let's start with the easier challenge,
Yeah.
and I think visual processing can help us there.
So on visual processing, that is already there with these models because they can generate images, or is it not there right now?
Well, what I'm alluding to is visual thinking. So
Okay.
yes, you process vision,
Yeah.
but you're able to think. So you can, for example, if you're a predator and you see your prey in a location in front of you,
Yeah.
then you process that and say, yeah, I need to go towards the prey
Yeah.
because I'm hungry.
Yeah.
Um, so so that kind of visual that processing that comes to visual thinking,
Yeah.
that is a sort of early stage of consciousness. Yeah.
Oh my goodness, this is mind blowing. You are incredible. You are deep. Oh my goodness. This is probably one of the best episodes that we have done, Michael. So thank you so much for being here. I don't
Yeah,
know if you're going to
thanks.
have any sort of closing advice and if you have anything that you want to share with the audience.
uh
Um,
well, yeah, just be positive. I mean, we haven't talked about the downsides, we haven't talked about hallucinations.
yeah.
Yeah, obviously, and there's downsides to AI, the danger to jobs, the dangers use of AI in warfare. There are downsides, but I am a technology optimist. You can probably gather that from our chat today. And I think that as long as we build safeguards, we
Yeah.
have United Nations to control misuse of AI. I think as long as we have that and we work together as a community, we can just bring out the positive in AI. And I think that's really what we should focus on.
Yeah, thank you so much once again for sharing your knowledge and wisdom. It's amazing, and I would love to bring you on maybe some other time. Maybe we can discuss on some other topics. So
Sure.
thank you so much, Michael, once again for sharing your knowledge.
Thank you, Sam. I enjoyed it. Thanks so much.
Of course, and to the audience, if you joined for the first time, this was part of our interview series for which we meet, some Fridays, not every Friday, between 8 a.m. to 11 a.m. Eastern. So make sure you guys are going to be watching my wall. That's where we publish these episodes. On that note, thank you so much, everyone, for tuning in today.